Welcome back. In the previous video, we found the Laplace transform of an exponential e raised to minus at. We'll take another example, then we will make some conclusions. And this time round, we'll again have an exponential x of t is equal to e raised power minus at, but in a slightly different form. So my signal is minus e raised power minus at u of minus t. Okay? U of minus t, it is a folded unit step. So your unit step u of t normally exists between 0 and infinity, which means u of minus t will exist between minus infinity and 0. Now if I try to find out the what you call Laplace transform of this, so we'll define x of s as minus bahar minus infinity to infinity e raised power minus at u of minus t, then its own factor of e raised power minus st dt. अब चूंकि u of minus t है, it means हमारा जो limit है, it is between minus infinity to 0. Then I can combine the two exponentials like this. Right? So it will be 1 upon s plus a. This minus will cancel out. Then again we'll have a factor like this, s plus at between the limits minus infinity to 0. Now here is the thing. When you proceed to upper limit 0, it's fine. It will be 1 by s plus a. Upper limit आप देंगे regardless of what s is, what a is, what kind of relation they have, it will still be e raised power 0. But when you proceed to lower limits, it will affect. Now you have to ensure here कि ये जो आपका सारा का सारा argument है, it has to be a positive quantity. Because जब ये positive quantity होगा, then you will proceed to limit t tends to minus infinity. Then only it will become e raised power minus infinity. Which means we have to ensure here that s plus a should be less than 0. In other words, s should be less than minus a, which means sigma should be less than minus a. Okay? And when you do this, you will see that it will be simply 1 by s plus a. Now this is an interesting fact here. Earlier we found Laplace transform of e raised power minus a to u of t. Algebraically, equation के हिसाब से it had a transform 1 by s plus a. Now we found the Laplace transform of another signal e raised power minus a t u of minus t. Mathematically speaking, इसका भी Laplace transform यही है 1 divided by s plus a. But the values, the range for which it converges, it changes. It is for sigma less than minus a. Now this is an important point with respect to the Laplace transform. Using these two examples, we actually see that algebraic expressions for the Laplace transform is identical. However, the set of values of sigma, आप कह सकते हैं, the set of values of s for which the expression, for which this transform converges, it is different. Right? So this is an important point here. Okay, apart from the algebraic expression, apart from knowing what is the Laplace transform of a particular signal, you also need to know the values for which this transform converges. Right? Because these are two different signals. This is a separate signal, this is a separate signal. दोनों का transform same आ रहा है 1 by s plus a, 1 by s plus a. Right? But Laplace में, this is a very important factor that apart from the expression, what your transform is, you need also to specify कि वो कौन से values है sigma के जिसमें आपका जो transform है, it is defined in the sense that it converges. Fine. So we define a term here what is known as the region of convergence. This is a very important term with respect to Laplace transform. And you will see later we'll be using this region of convergence to determine the properties of our systems. Right? So how we define region of expression is that it is basically the range of values of S, या आप सिग्मा कह सकते हैं इस केस में, या रियल पार्ट ऑफ S, whichever the way you want to put it. So the range of values of S for which the Laplace transform converges is referred to as the region of convergence, right? And this is an additional thing that you have to mention whenever you do the Laplace and Fourier transform. You just found out the expression, क्योंकि आप चेक पहले ही करते थे कि whether it satisfies those direct conditions, whether it's especially the condition whether it's absolutely integrable, right? अगर integrable नहीं था तो obviously it was, I mean, in 9 out of 10 cases you won't be able to find the Fourier transform directly, huh? You can use another properties, उनके थ्रू आप कर सकते हैं, but directly using direct expression you may not be able to find the Fourier transform. But in Laplace transform you will be finding you don't have to satisfy actually the Dirichlet conditions, but you have to specify what my region of convergence is, what are the values of sigma for which this transform is actually converging as a finite value. Okay? So this is region of convergence, and a convenient way of expressing this region of convergence is we define, it's a graphical representation, we define an S-plane. And S-plane is nothing, it is basically a plot of sigma and j omega. So I have a plane जिसका एक vertical axis है, जिसका एक horizontal axis है, and horizontal axis is my real axis sigma, and this is my imaginary axis j omega. And इस space में, इस S space में, I basically try to show my region of convergence. As an example, we had done two examples. तो पहला एग्जाम्पल हमारा ये था Laplace of e raised power minus a to u of t. इसका Laplace transform 1 by s plus a, but it was defined for sigma greater than minus a. So we locate a point minus a somewhere here. It will be, मान लीजिए यहाँ पे एक point है minus a, and draw a small line here. Something like this, and the way we show our region of convergence is like this, that is sigma greater than minus a. So ये जो सारा portion है that lies to right of this axis, this is my region convergence, means इस region में मेरा जो Laplace transform है, it is perfectly defined in the sense that it perfectly converges. So we show it like this. And the region which is left to this minus a, यहाँ पे आपका transform defined नहीं है, यहाँ पे आपका transform, it will not converge. So this is basically region of convergence sigma, it is greater than minus a. This is for the first example. Similarly जो हमारा second example था this, although उसमें भी algebraic expression same था, but if I try to show the region of convergence for that particular case, again I will have to draw an S-plane. This is my imaginary axis, this is my real axis, then I have to locate a point. So this is j omega, this is sigma, and its region of convergence is less than minus a. So somewhere here I will have a point minus a, so this point will have a vertical axis, and the region which is left to this vertical axis defines the region of convergence for that particular signal. Okay, so something like this. Fine, so this will be the region of convergence for our second example. Now you can see that algebraically आपके दोनों expression same है, so you can't differentiate between the transform of these two signals. But once you plot the region of convergence, you can now easily differentiate between these two. And later on, like I said, we will be mapping these region of convergence to the system properties. वहाँ पे then looking at the ROC of your particular system, you will be able to tell whether your ROC is stable, whether the ROC, yeah, the system for which you are plotting this ROC, whether that system is stable, whether that system is causal. Fine, just by looking at the ROC. Okay, so region of convergence, it has a lot of significance in the Laplace transform. It tells you a lot about the system जिसका आप analysis कर रहे हैं. Okay, so let's take another example. And in this example, we have a signal x of t 3 e raised power minus 2t u of t, and we have another component 2 e raised power minus t u of t. Okay? So it's a combination of two exponentials, right? And we need to find its Laplace transform. Not only algebraically, but we're also interested कि इसका region of convergence कैसा होगा. ठीक है? Okay, so x of s, it will be minus infinity to plus infinity. मैं directly signal लिख रहा हूँ minus 2t u of t, then minus 2 e raised power minus t u of t. Okay, then we have the factor e raised power minus st, and the integral is with respect to t. So we can separate this thing into two integrals. इसका separate लेते हैं क्योंकि u of t है, तो both the integrals will be from 0 to infinity. So this thing right here will be e raised power, I'm skipping some steps, to plus st dt, and this one will be minus 2. Again, the integral is from 0 to infinity, e raised power minus 1 plus st dt. ठीक है, तो इसका आएगा -3/2 plus s, and then here will be e raised power minus 2 plus st between the limits 0 and infinity. Then we will have plus 2/1 plus s, then e raised power minus 1 plus st between the limits 0 and infinity. Now again, दोनों cases में you have to look for the convergence. ठीक है, तो इस case में we have to ensure that -3/2 plus s e raised power minus infinity minus e raised power 0. Fine. Now this is possible only when you make sure कि आपका जो sigma है, because this quantity needs to be positive, so 2 plus s has to be greater than 0, which means s should be greater than -2, या आप कह सकते हैं sigma should be greater than -2. ठीक है, इसी तरह यहाँ पे it will be plus 2/1 plus s e raised power minus infinity minus e raised power 0. तो इसके लिए you have to ensure that sigma is greater than -1. Then when you will combine it, it will be, इसका तो आएगा 3 divided by s plus 2, इसका आएगा -2 divided by s plus 1. ठीक है, तो फिलहाल के लिए we'll stop here. As far as algebraic expression is concerned, we will have 3 by s plus 2 minus 2 by s plus 1. So right now the analysis has been done separately. So we have if we have done this thing, इसका हमने separately देखा, and it turns out इसका Laplace transform is 1 by s plus 2 with a region of convergence. We typically show it like this, sigma greater than minus 2. ठीक है. Then this thing जो इसका दूसरा component था e raised power minus t u of t, it was 1 by s plus 1 with a region of convergence sigma greater than minus 1. ठीक है. But we have to find the region of convergence of this, and that basically will be the intersection of the two region of convergence. So if I use black, if I plot, this is my, just a second, all right, this is my vertical axis, j omega axis, say this is my sigma axis. Okay, and I have to locate points minus 2 and minus 1. So let's put minus 2 is here, या थोड़ा बड़ा बना देते हैं, minus 2 is here. तो इसके through I will drop a line. Then I have another one minus 1 for the second one, so it is here. Again इसके through I will drop a line. Fine. अब जो इसका region of convergence है, it will be this area. I mean right to this point, huh? To the right side of this particular point through which we have drawn this vertical line. ठीक है, so ये सारा portion, this will be the region of convergence. इसी तरह if you try to plot the region of convergence of the second exponential which I have showed in red, that will be right to this point, huh? This line, इसके right में जो area आ रहा है. And overall जो आपका region of convergence होगा, it will be basically the intersection of the red and the blue region. So which is basically this part जो red में है. Fine, because if you find a combination sigma greater than minus 2, sigma greater than minus 1, जो intersection part है, it basically starts from to the right of this part, and this is basically sigma equivalent to minus 1. Okay, so I can say that we'll further elaborate this mathematically. So x of s is 3 divided by s plus 2 minus 2 divided by s plus 1, और जो इसका region of convergence है, it is for sigma greater than minus 1, because this is the intersection part of the two ROCs, and this is obviously greater than minus 1. Okay, fine. Now let's try to further simplify it. X of s फिलहाल हमने separately लिखा था. You can combine this, so it will be 3 times s plus 1 minus 2 times s plus 2 divided by s plus 2 and s plus 1. आप अगर further factorize करेंगे, मैंने यहाँ पे करके रखा है, तो ultimately it will be something like this. Plus 2, this will be your Laplace transform, and region of convergence will state this. Now this means, although हमने example के through किया, so I can kind of generalize here कि generally speaking जो Laplace transform है, it is a rational. Means आपका x of s, it will have a numerator polynomial n by s, जैसे यहाँ पे ये है. It will have a denominator polynomial d of s, जैसे यहाँ पे ये है. Now again you may be knowing this कि जो roots है numerator polynomial के, we call them zeros, because those values of s will make sure कि आपका जैसा x of s है वो zero आ जाए, वो zero बन जाए. That's why we call them zeros. And roots of your denominator polynomial, they are known as poles. because when you find these roots, उन roots पे आपका जो denominator polynomial, it will become 0, which means x of s will become infinite, and infinity is a pole. Fine, जहाँ पे इसका value infinite जाएगा, we technically say that it is a pole. Okay? So roots of numerator polynomial, it's called the 0, and roots of the denominator polynomial, we call that the poles of the x of s. Okay? We'll stop here. Next video we will discuss certain properties of the region of convergence with respect to these zeros and poles.